Hello. So in this video I'm going to discuss about using of Multiperceptron model. For this purpose I'm going to use the dataset MNIST, which can be taken from this TensorFlow.Keras.datasets module, and MNIST dataset is available to us. It is a dataset of handwritten digits from 0 to 9. You can see at this link also. So this is the original link, and we have 60,000 images in training, and there are 10,000 images in testing. We will see it when we will be running our code. Now let's go back. So in this I'm going to use TensorFlow version 2.x by default. So let's import it and check if it is taking 2.x. Yeah, so this version is 2.2, so it is 2.x version only. And now I'm going to import the dataset using this tf.keras.datasets.mnist. If I want to change my dataset, I can simply replace this .mnist function with some other, such as cfar10 or the fashion mnist, so or imdb, something like that. So this can be replaced and a different dataset can be picked. So I'm going to do it. So after getting the dataset, we want to define the training test set along with their labels. So the thing is that in the training folder we have 60,000 images for 0 to 9. So the I hope that you know what are training images and the labels. So if there is, imagine there is a image of 0, you want to give it as a training image, but the label for it will be 0. So we want to predict a 0 for it. Similarly, if there is a 1, we want to predict 1 for that image. So let's define the training images, test images, and the labels. So all of this can be done by a single function called mnist.loadData. So using this dataset name, we can simply use this loadData function and easily get this dataset into the training images, test images. You can look here also in this highlighted section. There are 60,000 images of 28 into 28 in the training dataset, and 10,000 images are there in the testing dataset. So all of this comes into these 4 variables, and after that we want to do the normalization also, because we do not want that the values of pixels should be in the range 0 to 255, but we want to normalize it to maybe 0 to 1. All the pixel values are divided by 255 to make the values between range 0 to 1. So after running this, our training image, training label, test image, and test labels are defined. After that, I want to check the number of images available in the training images and test images. So they are 60,000 and 10,000. Now I want to define the model. So for defining a model, we can simply write this sequential function, and within that we can define multiple layers by using these 3 words, tf.keras.layers, and by changing the functions so such that this flatten. What does this flatten do? Flatten, it flattens the input. Okay, so it does not affect the batch size. It's written here. So if inputs are shaped and without a channel dimension, then flattening adds an extra channel dimension, and outputs are batch comma 1. So you can read more about it. So right now I can only say that we are flattening the image, so because I want to convert the image into a 1D array. Alright, so after that we are giving this dense layer. So what is dense? Dense implements the operation, and you can read the details. It is taking 32 units. So these are the 32 units of neurons which will help you in training your model. Okay, so this is a hidden layer because it is a hidden layer. Why? Because classification layer is this one. So these are the 10 units which are defining the number of output classes, which is defined by a softmax function. So for a binary function we need a sigmoid layer. So if my number of classes are more than 2, then softmax function comes into play, and softmax is the activation function in which there is a array of all the classes, and to a particular class probability number is given. So the sum of all the probabilities in that array is 1, but the class having the maximum probability value is the class which is predicted. And so after defining this sequential function, I also want to compile my model using this optimizer Adam. So Adam, so it is a adaptive moment model. So my loss function is sparse categorical. Why? Because we have more than two classes, so I am going to write sparse categorical cross entropy here, and for the matrix purposes we are going to measure the accuracy. After that, we are going to define our callback function after defining the model and the compile function. So we are going to define callback function using the on epoch end function, which will help us stop the training after the training accuracy has reached 95%. Why? Because it saves time, right? We do not want to train it longer. So we will also be using this callback equal to my callback. So this callback is the object of class my callback. Alright, so after defining this, we are going to train our model using the model.fit function. We are going to pass the training images and the training labels into it. We are going to train it for 5 epochs, and we are going to pass this callbacks equal to callback, so that we can use the class my callback and stop our training after reaching 95% accuracy. So after epoch 1, our accuracy is improving. Yeah, so at the end of first epoch, 35% is the loss and 90% is the accuracy. Similarly, after epoch 2, our accuracy has reached 94%. After epoch 3, accuracy has reached 95.6%, so it has crossed 95%. We do not need to go do the fourth and the fifth epoch, so we will be early stopping. So this technique is called early stopping. Alright, so my final loss value is 14% and accuracy is 95%. And now I want to do the test loss. I want to check it on the test images. So what is the value of the test loss? So my validation accuracy is 95%. This is how MNIST digit based multi-perceptron training is done, and the final accuracy has been achieved as 95.86. Thank you for watching.